Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to another week of our NPTEL on nonlinear and adaptive control. For all of those who have been following this lecture series, we are entering week number 9 in the course, and all this time we have always been motivated by our desire to develop algorithms that will drive uncertain autonomous systems, very much like what we see in the background, which is a SpaceX satellite uh, orbiting the Earth. Now, I would like to welcome you again to week number 9 of this NPTEL. I am Shrikant Sakumar from Systems and Control, IIT KANPUR. So, just to give you a quick recap as to what we were doing just in the preceding set of lectures, um, what we had looked at to begin with, starting lecture 8.3. Of course, before that, we did, several other interesting topics like model reference adaptive control. Um, but in starting lecture 8.3, we moved to talking about the extension of the adaptive integrator backstepping to the vector case, right? So this is what we were looking at, and we saw how things don't change significantly in the vector case except for a little bit of bookkeeping that is involved, right? And we were able to design nice adaptation and feedback laws so as to stabilize this system. We were, of course, looking at the unmatched parameter case, and we did realize that having two estimates per parameter was a rather significant constraint for real implementation. And so we started to look at the extended matching design. Yeah. So what was different in the extended matching design, if you all remember, was that we don't define or declare the update law in the first stage itself, but we rather wait. And when we define the complete candidate Lyapunov function V, that is when we actually define the update law theta hat dot. And this way we have only one uh, parameter estimate for an unknown parameter, right? And so of course we go back to the what is expected, that is you just have one estimate per parameter. And what we realized also was that this estimate that you get is in fact the sum of our previous estimates, right? So we had two estimates earlier. I apologize. We had two estimates earlier, and this turns out to be the sum of those two update laws, right? So that's also interesting to see. Now, one of the issues that we did point out was that although the estimates was nice, there is only one estimate per parameter, which turns out to be the sum of the previous estimates, which is all nice. But what is hidden and not very evident is that the feedback law contains the theta hat dot, right? So there is, and we understood that there is one derivative per level of uh, unmatchedness. Yeah, so I'm sorry for using a cooked up word, but the control appears exactly one level below the unknown parameter, and therefore you have a theta hat dot. If the control appear two levels below, there would be a theta hat double dot, and so on and so forth. And having these successive derivatives of theta hat is not very healthy for any control implementation. All right, so this is one of the issues of the extended matching design. But in any case, it did help us alleviate the earlier issue of having two parameter estimates per parameter, right? So Then what we sort of wanted to or started to look at in the subsequent lecture was an example. Yeah, because I mean, all of us do want to know how these things do get applied. So this was sort of a cooked up example. We first did the matched case, meaning that the uncertainty was in the same dynamics as the control, right? And this was the vector case because a lot of us may not have had a practice to deal with the vector case. And we saw that its things are not significantly different. I mean, it's just that you use norms, right? Instead of using squares of scalars, you use norm squares, right? And that's pretty much the only difference. You have to be careful about taking transposers and careful of the sequence of things. You cannot flip around, move around things, just like you would do in the scalar case. But other than that, it was rather straightforward, right? So the matched case is what we had completed. And then we had started looking at the unmatched case, right? And that's where we will, of course, begin again, right? So I'm going to sort of start marking this again. I'm going to mark it again here simply because I want to discuss the unmatched case quickly again. I'm going to mark the lecture here, and this is the first lecture of the ninth week. Yeah, so we are well into our course in adaptive control. All right, so great. So the unmatched case dynamics, again, these are cooked up dynamics, but you will later on see in your assignments and homeworks and exams and I mean all sorts of things that similar dynamics appear in several places, several real systems. So it's not so far-fetched after. All right. So we have again two systems. X1 dot is fx1p plus x2, and x2 dot is omega cross x2 plus u, where x1, x2, and u and omega are all in R3. They are all vectors in R3. And fx1 is a 3 by 3 matrix. P is also in R3, and in this case, because we are considering the unmatched case, P is assumed to be unknown, while omega is assumed to be known. So it was sort of flipped of the matched case because in that you had something unknown here and everything was known here, right? So how do we go about this? We are first doing the standard adaptive integrator backstepping design where you have two estimates per parameter, right? So how do we do that? We start off assuming that P is unknown. We don't look at the known case and unknown case because I think all of you are now well exposed to the steps. So it's not very difficult to now skip some of these steps, right? So we start with the unknown P case and we just look at this piece of dynamics, like in the adaptive integrator backstepping. And the first thing we do is we define a candidate Lyapunov function. The best choice is, take a norm square for the first step. And you, of course, take, a p tilde squared term, 1 over 2 gamma p tilde squared type term, right? Because this is essentially, this is the parameter error here. Okay, this is the parameter error. And now what we declare what is our desired value of x2, right? Because we think of x2 as the control. So that is the x2 desired. How we declare it is we just take fx1 p hat because we cannot use a p being unknown. So we just use the estimate instead. So it's minus fx1 p hat and we introduce a good term, right? Now we sort of continue the Lyapunov analysis assuming that x2 is in fact equal to x2 desired. Yeah, so that's how we do. That's how we implemented the adaptive integrator backstepping, right? So let's diligently take v1 dot. V1 dot is just x1 transpose times x1 dot, which is now fx1p from here plus x2 desired, which is minus fx1p hat minus k1x1, right? And then you have this from the second piece, you just have minus 1 over gamma p tilde transpose p hat dot, right? So let's see if I can make this smaller. Yeah, right. So this is the second piece is from minus 1 over gamma p tilde transpose p hat dot. This is from the fact that p tilde dot is minus p hat dot. Okay, so that's just being applied here. Now you can see that I get a nice term here, minus k1 norm x1 squared, right? And here I get fx1 p tilde. So I get x1 transpose fx1 p tilde and minus 1 over gamma p tilde transpose p hat dot. Right? Now you can see that there's a p tilde here, there's a p tilde transpose here. I know that this entire thing is in fact a scalar quantity, right? Because v1 is a scalar, so therefore this each term is a scalar. So I can take a transpose and nothing changes. So I get p tilde transpose f transpose x1, and I can take p tilde transpose common, and I will just implement p hat dot as gamma f transpose x1. All right. And once I do that, once I implement this parameter update law, p hat dot, I will get my v1 dot as minus k1 x1 norm squared, which is negative semi-definite, right? So great. So we have, obtained the first parameter update law and the first Lyapunov, candidate Lyapunov. Right? Now, what is the next step? Now we know that x2 is not actually equal to x2 desired. So the next step is about creating a backstepping error variable. That's this guy. And that's just x2 minus x2 desired, which is exactly this, right? So we know that x2 desired also brings in the parameter again. So we are going to compute z dot, the dynamics of the backstepping error variable first. So what is z dot? It's x2 dot, which is these two terms. And then I have an x2 desired dot, right? So what is this x2 desired dot? X2 desired dot is just this guy. X2 desired dot is just this guy, which is del f del x1 times x1 dot and k1 x1 dot. Okay, so I have combined the two, del f del x1 dot plus k1 x1 dot. I have combined into these terms because x1 dot is just this guy. All right, and then I have a fx1 p hat dot. That's this. Okay, and I already know what is p hat dot because I've already designed it. So I substitute for it, and this term comes out to be gamma fx1 transpose x1. Okay, great. So now I know what's happened. I have already defined the p hat dot, but the unknown quantity p appears again. Okay, the unknown quantity p appears again, and this is what is going to create a problem when I design the controller. I cannot use a p hat again. I need to create a new estimate, and we call it p bar. Okay, and what's the idea of the adaptive integrator backstepping? It's that you take the earlier candidate function, add to it a norm squared term in the backstepping error, and a norm squared term in the new parameter error. Okay, the new parameter, that is p minus p bar squared. So you can see that this is exactly, I even showed it to you last time, this is exactly the new function v. Let's see if it's not here. So this is the extended design, but in the original design, this is the new one. So earlier v, then a norm squared term in the backstepping error, then a norm squared term in the new parameter error. Here there is a weighing matrix. Instead, I have just used instead of S, a weighing matrix, I've just used a scalar. Right? I've just used a scalar delta. Okay? So that's okay. You can choose a matrix or keep a scalar, your call. Yeah. Having a matrix, of course, gives you more handle on the adaptation game. Yeah. So that's more general. So once I have this V, I'm going to diligently take derivatives again, right? And then using that, I will try to give an update law p hat dot. That's the idea, because everything else is more or less chosen. We will of course choose some things here. Let's go forward and see what we need. So v dot is first v1 dot, right? So v1 dot is, let's see, it's x1 transpose x1 dot, which is fx1 p plus x2 plus you had a 1 over gamma, in fact there will be a negative sign, minus 1 over gamma p tilde transpose p hat dot. That is your v1 dot. And this is just copied from here. Yeah, this is just copied from here. I mean, of course, here you had plugged in x2 desired, but I'm not plugging in x2 desired because x2 is not actually equal to x2 desired. I just keep the x2 as it is. Everything else is just this. Okay. Right. Right. So I have this, and then I have a z transpose z dot, which I can plug from here, omega cross x2 plus u plus, I will write this as del f del x1 plus k1 fx1 p plus del f del x1 plus k1 x2 plus gamma fx1 transpose x1. This is just z transpose z dot, and then I have minus 1 over delta p minus p bar transpose p bar dot. All right. All right. So here again for p hat dot, I can substitute this quantity gamma f transpose x1. Right. So that's what I do. I will erase this. And this becomes p tilde transpose f transpose x1. Correct? Yes. Yeah. So here, of course, I've substituting for p hat dot. Okay. After substituting for p hat dot, this is what you will get. Okay. Great. Great. So now I use the usual tricks, right? What I will do is I will write x2 as z plus x2 desired, right, in terms of the backstepping error variable, and that is z minus fx1 p cap minus k1 x1. Okay, so this goes in here. So what will happen? I will get v dot as equal to minus k1 norm x1 square. This is from this term and this term together. Then I will get plus x1 transpose z, that's from this term and this term, and then I will finally get plus x1 transpose fx1 p tilde, and that's from this term and this term. Okay, and here I had minus p tilde fx1 transpose x1, and that's just rewriting this term here. Okay, and now let's see what I'm also going to do before I'm going to actually move this downwards. Right. Because what I'm going to do is I'm also going to choose my control. Right. How do I choose my control? I just choose my control to cancel whatever I can and do my best and introduce a good term. Right. So I'll choose my control as minus omega cross x2 minus del f del x1 plus k1 x2 minus gamma f x1 fx1 transpose x1. So that takes care of this term, and this term, and I'm left with this guy, which I cannot actually cancel completely, but I can always introduce the estimate, First I introduce a good term, minus k2z, gives me the good term, and then I will introduce minus del f del x1 plus k1 fx1 and p bar, right? So because I cannot introduce the p hat or the p, which is not available, I introduce the new estimate, which is p bar, right? Which is p bar. So basically I am going to cancel this, introduce a good term, and get something like this here. So once I do this, right, once I have this, I will get my v dot, right, in a more simplified form. I get a minus k2 non z squared. That's because of this guy combining with this guy, right? And I will get a plus z transpose del f del x1 plus k1 fx1 p tilde. And that's from this guy combining with this guy. Okay, so sorry, so this is not p tilde because p tilde is p minus p hat. This is actually the p minus p bar. All right, so great. So what has happened now? Uh, I have a couple of nice terms. This is nice, and this is nice. All right, so I get a couple of nice terms, right? And then what? I also have some cancellations, right? Because this term and this term is the same, right? By the way, I missed writing one term, which is this last term. So this is of course there, minus 1 over delta. I'm going to write it as p bar dot transpose p minus p bar. I've simply taken this and taken a transpose, right? This is just transpose. Yeah, I can do that because these are all scalars. I can keep taking transposes. This is so that the p minus p bar appears on the right hand side in both of them. Yeah, because they are vectors, so I cannot reorder things the way I want. Anyway, so I have these two cancellations. These two are good terms, right? Okay. I think I missed something. Okay, I'm sorry. I missed something, right? I missed something. I also need to use my control to cancel this guy, right? So I can do that because this is actually equal to z transpose x1, yeah. And so if I just introduce a minus x1, right, so then z transpose minus x1 is minus z transpose x1, and that gets cancelled here, right? So I'll also have a minus z transpose x1 from the control. That will of course get cancelled too, right? So what I am left with is, I mean, of course, I now make a choice of my p bar dot as delta times fx1 transpose del f del x1 plus k1. Yes. Let's see, I should have an appropriate dimension. Del f del x1 plus k1. I'm going to say I, yeah, because this has to be the appropriate dimension, transpose times z. So suppose I make this choice, I know that these two will cancel out also. So I'll be left with v dot as minus k1 non x1 square minus k2 non z square, which I know is less than equal to 0. So by the way, I didn't even need to cancel this out. I didn't need to cancel this out with this additional term in the control, because you see that this is a mixed term in these two terms. So just by choosing a large enough gain K1 and K2, I could have dominated this term also. So that was the other choice, right? I did not necessarily have to cancel this with this choice of control here. Yeah, I could have removed this. And if you remember, I could have done a sum of squares to write this guy. So I'm going to, maybe I'll do that in red. Remove this term and then write this as less than equal to half norm x1 squared plus half norm z squared, right? And these get, of course, combined with this guy and this guy respectively. And just by choosing a k1 and k2 large enough, I can dominate this next term. So this term is not essential. So this term is not essential in the control law. So if you want, you can ignore adding this term. Just by choosing large enough gains, k1 and k2, you will be fine. Yeah. So once you have this v dot as negative k1 norm x1 squared and k2 norm z squared, you are done. All right. You have a negative semi-definite v dot, and you sort of have, you can actually prove that. I mean, just like in standard backstepping, you can prove that x1 and z go to 0 as t goes to infinity. And I know that z is nothing but x2 minus x2 desired. So it is z is x2 plus fx1 p hat plus k1 x1 plus k1 x1. So now you know that this guy is going to 0 here. This guy is going to 0. If f0 is 0, then this piece is also going to 0. So the only thing that remains possible is that x2 also goes to 0. Yeah, as t goes to infinity. Yeah, this is the only possible choice. All right. So that's it. So essentially, you have done your design, right? You designed just like you want. You designed two controllers. So you've designed one control. Control is just one. Yeah. You've designed two parameter estimates. Right? You designed two parameter estimates. One is the p bar dot, right? And the other one is the mu hat dot. Sorry, other one is the p hat dot, right? And you also have the combined Lyapunov function choice, which is this guy. Okay, so this is what happens in adaptive integrator backstepping, right? You have one combined Lyapunov function, one control law, and two parameter estimates corresponding to each parameter. All right, so this is what you would expect, and this is what we had promised. Okay, so great. So this is the adaptive integrator backstepping, the classical one. What we want to do next, and we will do it in the subsequent lecture, is basically the extended matching design, which sort of helps us to remove this additional parameter estimate. All right, so that is really the idea. So what did we look at today? We continued our problem on adaptive integrator backstepping for this vector concocted system. I hope all of us did get a fair idea of how to work with vector systems. And I really hope all of you get the message that it's not significantly different from the scalar case. Yeah. And we, of course, designed this adaptive integrator backstepping based controller. So we have two parameter estimates and one feedback law. But now, of course, we want to move towards removing this additional parameter estimate for the same system. So we will, in fact, go ahead in the subsequent session and start with an extended matching design for the same system. So I really hope that this sort of example is giving you a good exposure into how to do this design. And I really hope that all of you will be at this stage able to pick up problems from your own fields, own your systems, autonomous cars, suspension systems, satellite systems, electrical systems, biological systems, and start working on some adaptive control designs for these. All right, great. So this is where we stop now, and we'll continue. Thanks.